So let's continue our conversation with working with some of these. And so you can see this next example here, we're going to be using the power reducing formulas to prove an identity. So you want to use the power reducing formulas to prove that sine cubed of 2x is equal to 1/2 sine 2x, 1 minus cosine 4x. Now I know we have talked about using the most complicated first, and this has a lot of terms going on, so we might think, well, let's use this, but I want to use actually this left side and move to the right side using kind of a similar trick that we did on the previous example. And so what I want to do is I want to take sine cubed of 2x and I want to convert this. So when I'm looking at this, I'm thinking, you know what? If I could get that to be a squared, I could probably use the power reducing formula and get it down. So I'm just going to kind of separate off one. So I'm going to have sine times sine squared. And so you can see that to the first power times squared would give me back the cubed. And in doing this, I'm just going to kind of leave this sine 2x out front. This sine squared, I'm going to use the power reduction formula. And so this would give me 1 minus cosine over 2. Now let's consider this. When you're looking at the power reduction formula, you see that your theta doubles. And so if we were just using it in terms of theta, we would say, okay, well, that would be 2 times that. So if I am using this in terms of 2x, that means 2 theta would be equal to 4x. And so we're going to actually end up with a 4x here because it doubles that value that we had in the sine squared. So we've got our power reduction formula. So this is already looking a little bit better. This divided by 2 is the same thing as multiplying by a half. And so I'm just going to kind of separate that out because I'm trying to get it to look like the right side. And then this is all being multiplied together. So I'm going to bring that 1/2 out front. I'm going to put it in front of the sine 2x. And then I have 1 minus the cosine of 4x here. And so you can see that now I'm back to what I was trying to accomplish. And so this one, I guess, kind of goes against the grain with the fact of we talked about the more complicated side, and the right side definitely looks a little bit complicated there. But we actually went to work with the left, separate off a sign, use our power reducing formula accurately, and then just kind of rearrange. Now for part 4, we're going to be using half angle formulas to find exact values. So there is some proofs in your textbook if you'd like to look up that. And what they're going to be doing, you'll notice in the first half we worked with 2 theta, and then we went to theta, and now we're going to be working with alpha over 2. So instead of theta, we're going to be using alpha over 2. And we're going to kind of use this trick as we work some examples here in a minute. So again, if you check out your textbook within Canvas, you'll be able to see that the proofs of all 3 of these are present there. You can see that I'm ending up with the square root of 1 minus cosine alpha over 2. Now we have 1 plus cosine alpha over 2, so just a sign change. And then if you consider sine and cosine and how it relates to tangent, you can see how these turn out to be the same just without the over 2. Now when I'm looking at this, you do need to note that this plus or minus is going to depend on the quadrant you're in. So this depends on the quadrant you are in. So just be aware of that. And there is an equivalent here. We can relate this back to these, but this simplified up is also equal to sine alpha over 1 plus cosine alpha, which is also equal to 1 minus cosine alpha all over sine alpha. So tangent of alpha over 2 does have a couple of different ways that we can write this. Now, just like earlier, we've got a how-to here. It says, given a tangent of an angle in the quadrant in which the angle lies, find the exact values of some trig functions of the half of the angle. And so it says, draw a triangle. Determine the half angle formula. Substitute and simplify. So the first thing I want to do is I want to look at this example here. We're not going to have to draw a triangle or anything, but I just want to kind of work through and see how we can relate this to what we know. So what I want to do is I want to find sine of 15 degrees using a half angle formula. And so let's consider this. Isn't 15 degrees equivalent to 30 degrees over 2? Trying to relate what they gave me to a half angle. So I said, you know what, 15, that's the same as 30 over 2. So if I'm trying to find the value of sine of 15 degrees using a half angle formula, I'm going to consider this to be sine of 30 degrees over 2. So then I can accurately execute my half angle formula because you can see that this is going to be my alpha over 2. So this would be equal to the square root of 1 minus cosine of 30 degrees over 2. Now we know what cosine of 30 degrees is. This value right here we could find using our unit circle. And so we say this is equal to the square root of 1 minus cosine of 30 degrees is equal to square root of 3 over 2, all over 2 from the formula. Combining these two fractions together, I would get the square root of 2 minus the square root of 3 over 2, all over 2. So I could put this over 2's all together, so I get the square root of 2 minus the square root of 3 over 4. And the top may not square root, but 4 does. So ending with 2 minus the square root of 3 over 4. So you can see that this would not be an easy value to accomplish, but the fact that we have this half angle formula, we could relate our angle to the half angle, execute our formula, and get an exact value for what sine of the 15 degrees would be equivalent to. Now in this next example, we are going to follow the how-to, and this will be our last example for this section. What we want to do is use what they have given, just like we did at the very beginning of part 1 of this lecture. Use what they have given, draw a picture, relate it, then execute it. So first of all, it says tangent of alpha is equal to 8 over 15. And it says that this alpha lies in quadrant 3. So I'm going to draw it out here. Now remember quadrant 1, quadrant 2, quadrant 3, quadrant 4. So we're going to be lying in quadrant 3. Tangent is 8 over 15. So remember tangent is equal to, you got SOHCAHTOA. So my tangent is my opposite over adjacent. But if I'm in quadrant 3, I'm going to be looking at a negative x and a negative y, and that's why we got a positive value here. So this would be my angle. Here's theta. So you draw your angle theta in quadrant 3, you drop it to the closest x-axis, and that creates your triangle. Opposite over adjacent, so my opposite is 8, my adjacent is 15, and we know they're both negative because of the x-axis being negative, the y-axis being negative. Now we have an idea of this triangle. Now, if you follow through on this triangle and do your Pythagorean theorem, you can see that this is going to be 8, 15, 17. Again, just doing negative 8 squared plus negative 15 squared is equal to c squared. Your c comes out to be 17. So I'm just building all my building blocks here. Then I'm like, okay, well, there's my theta. But let's consider this. If I'm down here in this quadrant 3, then that means my alpha here, I guess I labeled it wrong, alpha here is actually between 180 and 270 degrees. And if I need the half angle, that means I really need the half angle one to work this out. Because see, I'm trying to find sine of alpha over 2. That means I would have to divide all of these by 2. And so then that would give me 90 degrees is less than alpha over 2 is less than 270 over 2, which is 135 degrees. So although the information that they gave me put me in quadrant 3, when I begin to look at the half angle, alpha over 2, my angle is going to fall between 90 and 135, so it's going to lie in a different quadrant. So let's keep that in mind, that alpha over 2 is actually going to be in quadrant 2 because it's between 90 and 135, and we're going to need to use that information. Now before we get going with sine of alpha over 2, let's also note that your sine of alpha is equal to, remember SOHCAHTOA would be opposite over hypotenuse, so it would be negative 8 over 17. Cosine of alpha is adjacent over hypotenuse, so we're looking at negative 15 over 17. And tangent of alpha was given, which was 8 over 15. Now let's get going with this problem. So they say, let's find sine of alpha over 2, and that's equal to plus or minus the square root of 1 minus cosine alpha over 2. That's just our formula. Now, I told you earlier that this is dependent on the quadrant that it lies in. Okay, we're going to come back to that in a minute. So this is going to be equal to plus or minus the square root of 1 minus cosine alpha, which we've already identified, negative 15 over 17 over 2. Start cleaning this up. So let's see. 1 minus negative 15 over 17 is going to be like 1 plus 15 over 17. So that yields 32 over 17 all over 2. And if I'm dividing by 2, I can keep it, change it, flip it, keep the fraction, change its multiplication, flip this one to 1/2. So this ends up giving me 16 over 17. We're going to have space here. The square root of 16 over 17 actually ends up being 4 over the square root of 17, square root of the top and bottom. Rationalize that out to get your radical out of the bottom, and you end up with 4 square root of 17 over 17. Now the whole way you consider this being plus or minus. But because this is in quadrant 2, let's go back to our picture here. Because this is in quadrant 2, if you think about your unit circle, I'll draw it over here. If you think about quadrant 2 in regards to your unit circle, all the x comma y values, remember, are negative x's and positive y's. So if I'm looking at sine of alpha over 2, we see that alpha over 2 is actually going to fall within quadrant 2. And all my sine values are y values. So that means really we're looking at positive here, not plus or minus. We're not looking at the negative. We're just looking at the positive. So this is a really good example of how, even though we used our reference triangle and we outputted our half angle formula, because alpha divided by 2 fell into a different quadrant, we would only need to use positive of this answer. If it had fell into one of these bottom quadrants, then we would want to consider the negative of this answer. So again, that goes back to why here with your formula it has pluses or minus, but it's all dependent on what quadrant you're in with that half angle. So kind of a neat problem going on there. Now to finish up the section, I just want to kind of sum it all up. This would be a really nice page to kind of print and use as you work through your homework. So you see our double angle formulas, and again, these are 3 different options. You just want to use the one that is relevant to the problem you're trying to work. You've got, look, we've got 2 thetas here. Now we move into thetas, our reduction formulas, and so it helps us to reduce from a power into a power of 1. And then we've got our half angle formula, so 2 theta, theta, now we have alpha over 2, and it helps us to work with half angles, and such as the previous problem, work with what we have to create a half angle. So I hope this helps. If you have any questions along the way, feel free to reach out to me and go ahead and get started on your 9.3 homework.